Hello there. My name is Sean, and today I'm here to talk to you about how mechanical metamaterials can be used to revolutionize the world around us. Imagine a material with 1/5 the density of styrofoam that could support 160,000 times its own weight. This nanostructure could revolutionize the auto industry by cutting down the weight of your vehicle, thus decreasing fuel consumption by as much as 20%. Same goes for the aerospace industry, and this could amount to a savings of billions of dollars annually and help cut global fuel consumption drastically. And all that to me means a happier planet. But whoa. Let's take a step back. First of all, we must ask ourselves, what is a metamaterial? Well, a metamaterial is a material assembly of multiple elements that derive properties from their structure that differ from the properties of the materials they are made of. So instead of typical materials, where the chemistry dictates their properties, for mechanical metamaterials, it's their geometric structure. Think of the Eiffel Tower. The truss structure gives it the strength to support the weight of the 300-meter tall tower. These static civil engineering properties from the macro scale are the same principles that are being carried down to the micro and even nano scale for these mechanical metamaterials. So let's take a look at one of the leading structures, the OCTET truss lattice. The inspiration for the microstructure comes from natural cellular materials like honeycomb and sea sponge. These materials employ negative space and structure to maintain material strength and achieve a lower overall density than a bulk mass of the same material. Unfortunately, however, these structures fail in that they all display anisotropic mechanical behaviors, meaning that their mechanical properties are dependent on the direction of loading. This is where the engineering came in. The OCTET truss uses this strut structure to distribute the load through a multitude of axial loadings, mitigating bending forces, and because of this, can undergo a much higher load per unit density than an unorganized structure of the same material. It's also important to note that once yielding begins, the elastic region of these structures can reach much higher strain values than the materials they are comprised of. Think of a typical ceramic. Typical ceramics have a very low strain to failure. Now let's take a look at this OCTET truss structure made from the ceramic alumina. This structure is undergoing a strain of 35% and returning nearly to its original form. The structure is dictating these properties by changing the distribution of the loading strategically. And these are the properties that make metamaterials so intriguing. But how on earth do you make such tiny structures? Typical construction of them is through microstereolithography, where a pattern of light in the shape of the structure is focused down to the micro scale and printed in multiple layers over time. But this manufacturing process stands to need some improvement. The cost to produce these structures is relatively very high compared to traditional materials. But with that being said, the future research of these materials can extend beyond the micro and nano scale to the millimeter and centimeter scale, where the strengths of these structures could be exploited, manufactured more easily, and all of this means that there's a chance for faster implementation into our everyday lives, potentially replacing the need for traditional, overly dense materials.